Now going straight on with our second example of trying to find the equivalent regular expression from DFA. Right, here's the DFA that you start with, a three-state machine, okay, a bit more complicated. Alphabet, obviously binary, just A and B. Okay, so here's your DFA that you start with, and so I've got 5 diagrams, so A, B, C, D, E, and each diagram, the next diagram corresponds to the result you get from ripping out one, removing one state at a time. Okay. Now, similar to what we did the first example. So your first step, you go from your DFA into the corresponding relatively simple process of finding the GNFA from it by simply adding the start state here and the single accept state. Now remember, the start state of your GNFA has a transition arrow to the start state of your DFA. Well, that's the start here, you can see, that's the start state of your DFA. So there'll be a transition arrow from the start state of your GNFA to the start state of your DFA. Okay? And the transition arrow is labelled with epsilon. Okay? So, and the accept states, plural, if there's more than one, of your DFA, they get transition arrows labelled with epsilon, like here and here. So states 2 and 3, they're both accept states in your DFA. Well, they have a transition arrow to the one accept state of your GNFA, that's this one, okay? And they too are labelled epsilons. So you have an epsilon arrow here and here, okay? So that is your GNFA that you construct just by adding 2 more states, the start state and the accept state, to your DFA, whatever it was. Okay? So from there to there is pretty easy. Right? You just add the S and the A, and you add these. Well, actually, there's more. Now this is now a GNFA, right? So strictly speaking, you should be adding transition arrows labelled with empty states, the 0 with a slash through it. If there are no connecting arrows to A. So, but they're not drawn here. But they're imagine they're there. I mean, they're there. The GNFA has them. Okay. So now we move on. So that's diagram B. That's the GNFA with your 2 states added. Now we rip out our first state. Let's say it's 1. Now I'm not going to go through that. Well, you remember me mentioning the previous session that the equivalent regular expression for this DFA is quite long. In fact, you're jumping ahead a bit, but here it is. It's here. So if I put all that in one expression, it's sort of wrap around to about here. It's almost half the square. So quite long. So the reason I'm saying this and jumping ahead a little is, well, there are a lot of details here, and I don't want to go in all the details. I think now you understand how to find the replacing label on transition functions when you rip out a state and you have to replace the label from state QI to QJ. Right? Now I'll do a few just to give you a taste. Alright, let's rip out. So rip out 1. So the 1's missing. So now how many things are going to get ripped out? Well, there'll be like 6 things get ripped out. But the state itself, and there's 1, 2, 3, 4, 5 transition arrows that are no longer there. So now every state, remember, has a transition arrow from every other state. So there'll be a 0 from, there'll be a transition arrow with a label null set, the 0, the stroke through it, from S to 2. Okay? So imagine dot 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 between S and 2. And that will correspond to your R4 from the previous session. Okay, so so between S and 2, so S and 2, because the one's gone now, so we've got this dot 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 transition from S to 2 here, that's here. So we need to update its label. Well, now, so R1 would correspond to epsilon. R2, well, it's missing, so its label would be the empty set. So R2 star, still the empty set. Okay? And then R3, well, that would correspond to A. Okay? So the new label from S to 2 would be R1, R2 star, R3, union R4. Well, R4 is just the empty set, so forget about that. R1 is epsilon, so you're concatenating that with R2, but that's the star of the empty set. So that nothing, and all you're left with is R3, which is A. Okay, so just A. So that's what this is. Okay? But when you're unioning with R4, which has no effect. So you just left with R3 in effect, which is A. So that's A. Okay. Well, yeah, I'll leave it there. Now I've put in all the details, from the text. So do this as homework. Okay. So you just do much the same thing that I've done. I've done several times now. So you should. I hope you followed it. So you hopefully able to do that for yourselves. Do it as homework. And fill in the details of these other labels. In other words, derive C, this diagram C, from B. And you get C from B by ripping out state 1. So you rip out the state, you rip out these 5 transition arrows. And then you relabel the transition arrow that goes from S to 2. Now what else now like S to 3, well yeah, I'll do one more. So from 3 to 2, so 3 to 2 becomes BA union A. Now why is that? Let's try and deduce that one, for example. From 3 to 2, so from 3 to 2, well you've got an A there. Now that doesn't change, because ripping out the one state, when you rip out these 5, but you don't rip out this one. So you've got you've got a transition from 3 to 2 labelled A. Alright. But what about this one? So from 3 to 1 to 2. Well, your R1 then would be B. Your R2 would be, well, looping back it's not, there is no loop back from 1 to 1. So in a GNFA you do have to have a loop back, a self loop on each state, except for these. So it would be labelled null set. Okay. So your R2 start will be null set start, so forget about that. And R3 would just be A. So you've got R1, nothing in effect, R3. So it'd be BA, right? BA. So you'll have a connection from 3 to 2 labelled BA, but you've also got this one, A. So you need to union that was one of the rules, part of the rules in GNFA. So you need to, so you'll have BA union A. There it is there. BA union A, which is that one. Okay? Alright, well after a bit of work, you get this whole thing. And then you rip out 2, and now the labels here, because they're getting longer, it ends up being quite enormous. So check, do it for homework and check that you do get this, right? So you go from this to this, and this regular expression labels this self loop here, and this one, because I ran out of space, I should put it over here somewhere, but this is the label that corresponds to this link, S to 3. Right? This is this one's. And then you finally rip out state 3, and you get the GNFA that just has 2 states, the start state and the accept state. And this long expression here, hold on, it goes is the label of this transition here, and it's that. And this is the last one. It's the only one transition error remaining because you only have two states now, and it's that regular expression that is the equivalent regular expression of this DFA. Okay, so do that for homework. Check the details to convince yourself that you understand how it's done. All right. Okay. New section 1.4, the last section in the chapter. Pretty short. It's only about half a dozen pages or so. A couple more theorems as usual. Right. Now you can guess, and you've said it earlier, but just from the title, non-regular languages. So a regular language, remember, is any language that is recognized by some finite automaton. Okay. So you can guess that a non-regular language is some language that is not recognized by a finite automaton. So let's do some examples. Now, the point of this chapter is to, well, there are various things, but one is to contrast a non-regular language from a regular language. So to understand what finite automata can do.